quiet archive record. Tonight, we're stepping into a slow unfolding. Settle in, let the outside world dissolve, and gently descend into tonight's world. Quantum physics is the set of rules used to describe nature at very small scales, where energy comes in discrete amounts, and where probability is not just a lack of knowledge, but part of the basic description. In this episode, we explain several quantum phenomena that have been tested many times and that shape real devices. We will move from quantization and interference to superposition, entanglement, tunneling, uncertainty, and a few related effects like the Casimir force and superconductivity. The goal is to keep the claims grounded, connect ideas to experiments, and separate what is measured from what is still debated. Tonight, we explain the most interesting quantum phenomena. Before we go deeper, here are a few simple ways to keep the ideas straight. First, think of quantization like a staircase, not a ramp. On a ramp, you can stand anywhere. On a staircase, you can stand only on steps. Many quantum quantities behave more like steps than ramps. Second, think of interference like overlapping ripples in a pond. Two ripples can add up to a taller ripple, or they can cancel and leave flat water. In quantum physics, it is not the material that is rippling. It is the probability amplitude that we use to predict where outcomes land. Third, think of superposition like a musical chord. A single note is one clean tone. A chord is a combination of notes played together. In quantum terms, a superposition is a combination of states that can later interfere, the way notes can combine to change the sound. Fourth, think of entanglement like two perfectly matched sets of answers created together. The answers are linked even when the pieces are far apart. It is not a message being sent. It is a link in the shared setup that shows up when you compare results. Fifth, think of decoherence like smearing fingerprints across a window. When too many interactions leave marks, you can no longer see a clean pattern. In quantum systems, interactions with the environment leave records that wash out interference. These analogies are not perfect, but they help you avoid the most common trap, treating quantum effects as random magic. The rules are consistent, and the surprises come from using the wrong, everyday picture. Start with a simple question. What is a quantum state? In classical physics, we picture an object as having definite properties at all times. A ball is at a particular place and moves with a particular speed. A planet has a position and a momentum. A circuit has a voltage and a current. With enough information, you can, in principle, predict what happens next. Quantum physics keeps prediction, but it changes the kind of information you can have. A quantum state is a mathematical object that lets you calculate probabilities for different measurement outcomes. It is not a direct list of properties that are definitely true. Instead, it is more like a compact rulebook that tells you the distribution of results you should expect if you measure position, or momentum, or energy, or some other quantity. This new kind of description is not a philosophical choice. It was forced by experiments. Early researchers tried to explain atomic spectra, the stability of matter, and the behavior of light and electrons. The classical picture broke down. The quantum framework replaced it, and then proved itself by making precise predictions. One of the first quantum phenomena is quantization. In many quantum systems, certain values come in steps rather than continuous ranges. Energy is the most famous example. In an atom, electrons do not orbit like little planets. Instead, they occupy allowed energy states. When an electron changes from a higher energy state to a lower one, the difference in energy is released as a photon. The photon has a specific frequency. This creates sharp spectral lines. Hydrogen is the simplest case. Its spectrum can be predicted with a small set of quantum rules. Those predictions match observed lines with great accuracy. For more complex atoms, the calculations are harder, but the same basic idea holds. Spectral lines are a direct window into quantized energies. Quantization also explains why matter is stable. If electrons could have any energy, they could radiate energy continuously and spiral into the nucleus. Atoms would collapse. Quantized states prevent that. The lowest energy state is stable. There is no lower state for the electron to fall into. In solids, quantization appears in band structure. When many atoms form a crystal, their electron states mix and split into bands of allowed energies. Between bands, there can be gaps where electron states do not exist. Conductors, insulators, and semiconductors differ largely by how their bands and gaps are arranged. A metal has available states near the energy electrons naturally occupy, so electrons can move easily when an electric field is applied. An insulator has a large gap, so electrons cannot move without a large input of energy. A semiconductor has a moderate gap that can be controlled by doping, light, or electric fields. This is the foundation of transistors and modern computing. Light emission is another place where quantization is obvious. In an LED, electrons cross a junction and then drop into lower energy states, emitting photons. The photon energy, and therefore the color, is set by the band gap. A red LED has a smaller gap than a blue LED. The development of efficient blue LEDs was difficult because it required materials with the right properties and fabrication methods that could keep defects low. The photoelectric effect is another classic quantum phenomenon. Shine light on a metal and electrons are ejected. Classical physics would suggest that brighter light should always eject electrons with higher energy, because brightness means more energy delivered. But experiments showed a threshold frequency. Below that frequency, no electrons come out, no matter how bright the light is. Above it, electrons are ejected, and their maximum energy depends on the light frequency, not on brightness. This behavior makes sense if light comes in photons, each carrying energy proportional to frequency. One photon interacts with one electron. If the photon does not have enough energy to overcome the binding energy of the metal, the electron cannot escape. Brightness increases the number of photons, and therefore the number of ejected electrons, but not the energy per electron. So far, the phenomena might sound like clever bookkeeping. Energy comes in steps, light comes in packets. The next set of phenomena is where probability and interference become central. Consider interference, a wave effect. Water waves overlap and form patterns of reinforcement and cancellation. Sound waves do the same. Light can behave as a wave, too. If coherent light passes through two slits, it produces bright and dark bands on a screen. The pattern is explained by adding wave amplitudes. Where the waves add, the screen is bright. Where they cancel, it is dark. Now replace light with electrons. Fire electrons one at a time through a double-slit apparatus. Each electron hits the screen as a single dot, like a particle. But after many electrons, the distribution of dots forms the same kind of interference pattern. It is as if each electron took both paths and interfered with itself. This is a core quantum phenomenon, single particle interference. The quantum state spreads over multiple paths, and the different paths can combine to change the probability of where the particle is detected. The interference pattern is a pattern in probabilities. A natural question is, which slit did the electron actually go through? If you place a detector near one slit to record the path, the interference pattern disappears. You get a distribution consistent with particles taking one slit or the other, without the fine fringes. This is not just because the detector bumps the electron in a crude way. It is because obtaining which path information changes the quantum state. When the path becomes recorded in the environment, the different path components become linked to different detector states. In technical terms, the electron becomes entangled with the detector. If you ignore the detector and look only at the electron position results, the interference is washed out. The phase relationship that makes the interference pattern is no longer available. This leads to superposition. A superposition is a quantum state that can be expressed as a combination of other states. In the double-slit experiment, the electron state can be a superposition of a path through slit A and a path through slit B. Before measurement, the theory treats both components as part of the single state used to compute probabilities. Superposition is not limited to paths. It applies to any set of states. An atom can be in a superposition of energy states. A photon can be in a superposition of polarization states. A superconducting circuit can be in a superposition of current states. What changes is how stable the superposition is and how hard it is to isolate the system. A famous thought experiment uses a cat, but real quantum physics does not require cats. It requires systems that can maintain coherent superpositions. In laboratories, researchers can create superpositions in ions, atoms, photons, and engineered circuits. They can measure interference between the components and show that the superposition behaves as expected. At this point, it helps to introduce the idea of measurement. In quantum physics, measurement is not just reading a value. It is an interaction that produces an outcome and leaves a record in some physical system. Many interpretations exist about what measurement means at the deepest level, but the operational facts are clear. When you measure a quantum system in a way that distinguishes outcomes, you get one outcome. The probabilities of the outcomes are given by the quantum state. Another phenomenon closely tied to superposition is decoherence. Decoherence is the process by which a quantum system loses its coherent phase relationships because it becomes entangled with its environment. The environment can be air molecules, thermal vibrations, stray electromagnetic fields, or internal degrees of freedom. When the environment records information about the system, even indirectly, the system's ability to show interference effects is reduced. Decoherence helps explain why macroscopic objects do not usually show obvious quantum interference. Large objects are constantly interacting with their environment. Their quantum states become entangled with countless environmental degrees of freedom. The interference terms become effectively unobservable. The system behaves as if it has a definite state, even though the full quantum description of system plus environment is still quantum. Decoherence does not by itself pick one outcome. It explains why certain superpositions become fragile and why classical behavior emerges in practice. It is a key piece of modern quantum theory and a practical challenge for quantum technologies. Now we can move to one of the most famous and most surprising quantum phenomena, entanglement. Entanglement occurs when two or more systems share a joint quantum state that cannot be written as a simple product of separate states. In an entangled state, the outcomes of measurements on one system are correlated with outcomes on the other in ways that cannot be explained by any local hidden variable theory, as shown by Bell's theorem and many experiments. A simple example uses two photons whose polarizations are linked. Suppose the pair is prepared so that if one photon is measured to be horizontally polarized, the other will be vertical, and if one is vertical, the other will be horizontal. Before measurement, neither photon has a definite polarization in the usual sense. Instead, the pair has a joint state that encodes correlations. If you measure one photon and get a result, you can predict the other photon's result with high confidence, depending on the measurement settings. This happens even if the photons are far apart. It might sound like faster than light communication, but it is not. You cannot choose the outcome of the first measurement, so you cannot send a controllable signal. The correlations appear when you compare results afterward. Bell tests take entanglement and put it in a strict experimental form. They measure correlations between outcomes under different measurement settings. If local hidden variables existed that predetermined outcomes, the correlations would satisfy certain inequalities. Quantum theory predicts violations of those inequalities for entangled states. Experiments repeatedly observe violations with increasing levels of rigor. Modern experiments close key loopholes, such as detector inefficiency and timing issues. The conclusion is not that causality is broken, but that the world cannot be described by local hidden variables in the classical sense. Quantum correlations are real. The joint state matters. Entanglement is not just a curiosity, it is a resource. Quantum cryptography uses entanglement to detect eavesdropping. Quantum teleportation uses entanglement and classical communication to transfer an unknown quantum state from one location to another, without sending the physical system that initially carried the state. Teleportation sounds like science fiction, but in physics, it is a protocol that has been demonstrated with photons and other systems. In teleportation, two parties share an entangled pair. One party performs a joint measurement on the system to be teleported and their half of the entangled pair. That measurement produces a classical result that is sent to the other party. The other party uses the classical result to apply a correction operation to their half of the entangled pair. After the correction, their system is in the same quantum state as the original. The original state is destroyed by the measurement, so no cloning occurs. This highlights another quantum phenomenon, the no-cloning theorem. It is impossible to make a perfect copy of an unknown quantum state. This is not a technological limitation. It is a mathematical consequence of the linearity of quantum evolution. No cloning is important for quantum security and for understanding why measurement changes the system. Next comes quantum tunneling, a phenomenon that is both strange and central to real technology. In classical physics, a particle facing a barrier higher than its energy cannot cross it. It would bounce back. In quantum physics, a particle has a wave function that can extend into the barrier. There can be a non-zero probability that the particle appears on the other side. This is tunneling. Tunneling is not a violation of energy conservation. The energy of the particle remains the same. The barrier is not climbed. Instead, the wave function decays inside the barrier and can re-emerge on the far side. The probability depends strongly on the barrier width and height. Thinner or lower barriers have higher tunneling probability. Tunneling explains alpha decay. In certain nuclei, alpha particles are trapped by the nuclear potential, but can tunnel out, leading to radioactive decay. The rates of decay can be predicted using tunneling models. This was a major success of early quantum theory. Tunneling also appears in scanning tunneling microscopy, STM. In an STM, a sharp tip is brought extremely close to a conductive surface. Electrons can tunnel between the tip and the surface. The tunneling current depends exponentially on the distance. By scanning the tip and keeping the current constant, the instrument can map the surface with atomic scale resolution. This is one of the ways we can literally image atoms. Another device based on tunneling is the tunnel diode. In certain semiconductor junctions, electrons can tunnel through a barrier, leading to unusual current voltage behavior, including regions of negative differential resistance. This can be used in high-speed electronics. Tunneling is also part of how some chemical reactions occur, especially involving light atoms like hydrogen. In enzymes, tunneling can contribute to reaction rates. The details can be complex, but the main idea is that quantum effects can matter even in biological contexts under certain conditions. Now consider the Heisenberg uncertainty principle. This is often misunderstood as a statement about measurement disturbance. Disturbance can matter, but uncertainty is deeper. It states that certain pairs of quantities cannot both be sharply defined in the same quantum state. The most famous pair is position and momentum. If a particle is in a state with very well-defined position, its momentum distribution must be spread out. If it is in a state with very well-defined momentum, its position distribution must be spread out. This is not because we are clumsy. It is because the mathematical structure of quantum states and operators imposes limits. The more you squeeze the wave function in space, the more you spread it in momentum. Uncertainty has measurable consequences. It sets the scale of the ground state energy of the harmonic oscillator. It helps explain why atoms have a minimum size. It influences phenomena like quantum pressure in electron gases and the stability of white dwarf stars, where electron degeneracy pressure supports the star against gravity. Closely related is the idea of zero-point energy. Even at absolute zero temperature, a quantum system can have residual motion. A harmonic oscillator has a non-zero ground state energy. This is again a consequence of uncertainty. If both position and momentum were zero, the state would violate the uncertainty principle. Zero-point energy is not an endless free energy source. You cannot extract arbitrary work from it without changing the system. But it does have real effects. One effect often discussed is the Casimir effect. The Casimir effect is a force between two closely spaced, uncharged conducting plates in a vacuum. The basic idea is that the presence of the plates changes the allowed modes of the electromagnetic field between them compared to outside. This difference in modes leads to a pressure that pushes the plates together. The effect is small but measurable. It becomes significant at very small separations. The Casimir effect can be described in different ways. Some descriptions emphasize vacuum fluctuations and zero-point energy. Others emphasize boundary conditions and electromagnetic interactions. The key point is that quantum fields and boundaries can produce a measurable force. Another set of quantum phenomena involves indistinguishable particles and statistics. In quantum physics, identical particles are truly identical in a way that has consequences. If you swap two identical particles, the total quantum state can either remain the same or change sign. Particles that remain the same are bosons. Particles that change sign are fermions. Bosons can occupy the same quantum state. This is why lasers work. In a laser, many photons occupy the same mode, producing coherent light. Bosons also allow Bose-Einstein condensation, where many atoms fall into the same ground state at very low temperatures, forming a new state of matter with macroscopic quantum behavior. Fermions obey the Pauli exclusion principle. No two identical fermions can occupy the same quantum state. Electrons are fermions. This principle shapes the structure of atoms. It explains why electrons fill shells and why the periodic table has the structure it does. It also explains electron degeneracy pressure in dense matter. Bose-Einstein condensation, BEC, is a striking quantum phenomenon. When bosonic atoms are cooled to extremely low temperatures, they can occupy the same quantum state. The cloud of atoms then behaves like a single quantum object. Researchers can observe interference between condensates and study superfluid behavior. Superfluidity is another quantum phenomenon. In a superfluid, a fluid can flow with extremely low viscosity. Liquid helium-4 becomes a superfluid at low temperatures. Helium-4 atoms are bosons, and their collective behavior leads to superfluidity. Helium-3, a fermion, can also become superfluid, but through pairing mechanisms similar to those in superconductivity. Superconductivity is one of the most important quantum phenomena in technology. In a superconductor, electrical resistance drops to essentially zero below a critical temperature. Superconductors also expel magnetic fields, a phenomenon called the Meissner effect. This leads to magnetic levitation demonstrations, where a magnet can float above a superconductor. The microscopic explanation of conventional superconductivity involves Cooper pairs. Electrons are fermions and usually repel each other due to their charge. But in a crystal lattice, interactions with vibrations of the lattice, called phonons, can produce an effective attraction between electrons under certain conditions. Electrons can pair up into Cooper pairs. A Cooper pair behaves as a boson, allowing many pairs to occupy a collective state. In the superconducting state, the pairs form a coherent condensate. There is an energy gap that makes it harder for scattering to disrupt the current. The result is a persistent current that can flow without resistance. Superconductors are used in MRI machines, particle accelerators, and sensitive magnetic detectors called SQUIDs, superconducting quantum interference devices. SQUIDs use quantum interference of superconducting wave functions in a loop containing Josephson junctions. They can measure tiny magnetic fields. Josephson junctions themselves are a quantum phenomenon. A Josephson junction is a thin insulating barrier between two superconductors. Cooper pairs can tunnel through the barrier. The tunneling current depends on the phase difference between the superconductors. This leads to the Josephson effects, including a supercurrent without applied voltage and an oscillating current under a constant voltage. These effects are used in voltage standards and in quantum computing. Many modern qubits are built from superconducting circuits with Josephson junctions. They use quantized energy levels in the circuit and maintain superpositions long enough to perform computations. Quantum computing relies on a few of the phenomena we have already described: superposition, interference, and entanglement. A qubit can be in a superposition of 0 and 1. Multiple qubits can be entangled. Computation is performed by applying operations that change amplitudes and phases. The final measurement produces a classical result, with probabilities determined by the quantum state. The promise of quantum computing is that certain problems can be solved more efficiently than on classical computers. Examples include factoring large numbers with Shor's algorithm, simulating quantum systems, and certain search and optimization tasks. The reality is that building large-scale quantum computers is extremely challenging because of decoherence and noise. Quantum error correction is a set of techniques to protect quantum information. It uses entanglement and redundancy across many physical qubits to encode one logical qubit. Errors can be detected and corrected without directly measuring the encoded quantum information. This is possible because different kinds of measurements can reveal error syndromes while preserving the logical state. Even without a universal quantum computer, quantum sensing and quantum communication are already practical. Quantum sensors can achieve very high precision by using quantum coherence. Atomic clocks, for example, use quantized energy transitions to keep time. The best atomic clocks are accurate to extraordinary levels, enabling GPS and scientific tests of relativity. Another phenomenon that often appears in discussions is the quantum Zeno effect. The quantum Zeno effect is the idea that frequent measurements can inhibit the evolution of a quantum system. If a system is repeatedly measured to check whether it is still in its initial state, and the measurements are frequent enough, the probability of leaving the initial state can be reduced. This effect has been observed in experiments. It depends on what counts as a measurement and on how the system is coupled to the measuring apparatus. In practice, it is related to the way interactions can suppress certain transitions. The related anti-Zeno effect can also occur, where frequent interactions can speed up transitions, depending on the details. The important point is that measurement-like interactions can change the rate of quantum evolution. Another phenomenon is quantum squeezing. In certain quantum states of light or matter, uncertainty can be redistributed between complementary variables. For example, for a light field, you can reduce the uncertainty in one quadrature while increasing it in the other, within the limits of the uncertainty principle. Squeezed light can improve the sensitivity of measurements. Gravitational wave detectors like LIGO use squeezed light to reduce quantum noise and improve detection. This is a direct example of quantum effects improving a macroscopic measurement. Quantum coherence also plays a role in lasers. A laser produces light with a well-defined phase relationship across the wavefront. This coherence is why laser light can produce strong interference patterns and can be focused tightly. The phenomenon of stimulated emission is the key to lasers. In an atom, if an electron is in an excited state, it can drop to a lower state and emit a photon. If a photon with the right energy passes by, it can stimulate the emission of a second photon that matches the first in frequency, phase, and direction. This leads to amplification of coherent light. Now consider a phenomenon called quantum confinement. When electrons are confined to very small regions, their allowed energy levels shift. This is similar to how a particle in a box has quantized energy levels that depend on the size of the box. In nanostructures like quantum dots, electrons are confined in all three dimensions. The size of the dot determines the energy levels and therefore the color of light emitted. Quantum dots are used in displays and lighting. They can produce bright, pure colors and can be tuned by changing their size. This is again quantization at work, but engineered at the nanoscale. Another important phenomenon is the quantum Hall effect. In certain two-dimensional electron systems at low temperatures and strong magnetic fields, the Hall resistance becomes quantized in precise steps. The quantized values are extremely accurate and depend only on fundamental constants. The integer quantum Hall effect can be explained by the formation of Landau levels, quantized cyclotron orbits of electrons in a magnetic field, and by edge states that carry current without scattering. The fractional quantum Hall effect is even more remarkable, involving collective behavior where the effective excitations can have fractional charge and anyonic statistics. These effects are important for metrology and for understanding topological phases of matter. They show that quantum behavior can create new kinds of order that are not captured by simple symmetry breaking. Topological insulators are another phenomenon in this area. A topological insulator is insulating in its bulk, but has conducting surface states that are protected by the material's topology and symmetries. These surface states can be robust against certain kinds of disorder. Topological phases are a modern frontier, but the core idea is that global properties of the quantum state can protect certain behaviors. This links quantum physics to deep mathematics and also to potential applications in robust quantum computing. Now return to a simple but powerful concept: the role of phase. In quantum mechanics, amplitudes can be complex numbers with phases. Interference depends on phase differences. Many quantum phenomena can be understood as controlling phase. In an interferometer, a particle's wave function splits, travels along two paths, and then recombines. The relative phase determines whether the recombination produces constructive or destructive interference in a given output port. This is used in devices like the Mach-Zehnder interferometer. In atom interferometry, atoms are used instead of photons. Atom interferometers can measure accelerations, rotations, and gravity gradients with high sensitivity. They can test fundamental physics and have practical applications. Another phenomenon related to phase is the Aharonov-Bohm effect. This effect shows that in quantum mechanics, electromagnetic potentials can have physical consequences, even in regions where the magnetic field is zero. In a classic setup, electrons travel along paths around a region containing a magnetic field confined to a solenoid. The electrons never pass through the field region, but the presence of the vector potential shifts the interference pattern. This demonstrates that the quantum phase can be influenced by potentials. This effect has been observed and is important for understanding gauge theories and quantum phases. Quantum phenomena also show up in the behavior of materials in surprising ways. Consider magnetism. In many materials, magnetism arises from electron spin and from the Pauli exclusion principle. Electrons have an intrinsic angular momentum called spin. Spin is quantized. It can take certain values and behaves like a two-level system in many contexts. Spin is not literally a tiny ball spinning, but it has measurable magnetic moments and obeys quantum rules. Spin is used in technologies like MRI and in spintronics. In MRI, nuclear spins in the body align with a strong magnetic field. Radio frequency pulses perturb the spins, and as they relax, they emit signals that can be used to form images. The quantized nature of spin transitions and their interactions with the environment are central to the method. In quantum information, spin systems can serve as qubits. Electron spins in quantum dots or defects in diamond, such as nitrogen vacancy centers, can be controlled with microwaves and can have relatively long coherence times. The nitrogen vacancy center in diamond is a good example of a quantum system that works at room temperature. It is a defect in the diamond lattice that creates a localized spin state. That spin can be manipulated and read out optically. NV centers are used for magnetic sensing at very small scales. Now consider the idea of measurement back action. When you measure a quantum system, you generally disturb it. This is not a technical flaw. It follows from the fact that measurement involves interaction. For certain measurements, back action can be minimized or controlled. Weak measurements, for example, allow partial information to be gained with limited disturbance, at the cost of increased uncertainty in the outcome. Weak measurements can be used to study quantum trajectories and to test subtle predictions. They do not violate the uncertainty principle. They provide a different window into how information and disturbance relate. Another phenomenon often discussed is delayed choice experiments. In a delayed choice setup, you decide whether to observe interference or which path information after the particle has entered the apparatus. Experiments show that the outcomes still match quantum predictions. The key lesson is not that the particle decides retroactively, but that the quantum description of the experiment includes the entire measurement context. The choice of measurement determines what type of statistics you observe. Quantum eraser experiments extend this idea. They show that if which path information is marked and then later erased in a way that makes the paths indistinguishable again, interference can be recovered in a conditional way. When you sort results by the appropriate measurement outcomes on the marker system, interference patterns appear. Without sorting, they average out. The takeaway is that entanglement and information determine whether interference is visible. It is about correlations and the availability of phase relationships, not about time travel. Now we can step back and ask why quantum theory uses probability. One reason is that the outcomes are not determined in the way classical theory suggests, at least not by local hidden variables. Another reason is that quantum theory is built on a linear wave-like evolution that produces interference. Measurement outcomes are discrete. Probability is the bridge between continuous amplitudes and discrete results. The Born rule is the rule that connects the wave function to probabilities. It states that the probability of an outcome is proportional to the squared magnitude of the amplitude associated with that outcome. This rule has been tested countless times. It is central to quantum mechanics. There are deep questions about why the Born rule holds and how to derive it from more basic principles. Different interpretations address this differently. But for practical purposes, the Born rule is part of the tested framework. Now consider one more quantum phenomenon with a strong practical impact: quantum noise. In classical electronics, noise can come from thermal motion, defects, and external interference. In quantum systems, there is also noise that arises from the quantized nature of energy and from uncertainty. Shot noise, for example, arises because current is carried by discrete charges. The arrival of electrons is a random process with a statistical distribution. Even if the average current is steady, the fluctuations are real. In light, photon shot noise affects measurements. In very precise optical experiments, the discrete nature of photons sets limits. This is why squeezed light can improve sensitivity. It can reduce noise in one variable. In quantum optics, there are many phenomena, like anti-bunching and single photon sources, that rely on the fact that photons are discrete and that emission events can be controlled. Single photon sources are important for quantum communication. Another interesting phenomenon is the Lamb shift, a small shift in the energy levels of hydrogen due to interactions with quantum electromagnetic fluctuations. The Lamb shift was a key early test of quantum electrodynamics. It showed that the vacuum is not empty in the classical sense. Fields have quantum effects. Quantum electrodynamics, QED, is the quantum theory of the electromagnetic field and its interaction with charged particles. It makes incredibly accurate predictions, such as the anomalous magnetic moment of the electron. The accuracy of these predictions is one of the strongest confirmations of quantum theory. At this point, it may help to connect quantum phenomena to the bigger picture of physics. Quantum mechanics is the framework for matter and light at small scales. Quantum field theory extends it by treating fields as fundamental and particles as excitations of those fields. In this view, the electron is an excitation of the electron field, and the photon is an excitation of the electromagnetic field. Quantum field theory explains particle creation and annihilation processes, and is necessary for high-energy physics. It also underlies condensed matter physics, where collective excitations like phonons and magnons can be treated as quasi-particles. Even if we focus on the experiments and devices, it is useful to know that quantum phenomena are not isolated oddities. They are part of a consistent framework that scales across many domains. Now consider a practical question. How do we make quantum effects show up? Often we need to isolate systems from their environment, cool them down to reduce thermal noise, and control interactions precisely. This is why many quantum experiments happen at low temperatures and in high vacuum. But quantum effects are not limited to extreme conditions. The quantization of energy in atoms produces spectral lines at room temperature. Semiconductors work at room temperature. LEDs and lasers work at room temperature. The quantum aspect is built into the material structure. The difference is that delicate phenomena, like long-lived superpositions and entanglement, are more fragile and often need careful isolation. Now we can summarize the main phenomena we have covered. Quantization. Energy and other quantities come in discrete levels in many systems, explaining atomic spectra and material properties. Single particle interference. Particles can show wave-like interference patterns even when sent one at a time, because probabilities arise from amplitudes that can interfere. Superposition. Quantum systems can be in combinations of states, leading to interference and new behaviors. Entanglement. Joint states can produce correlations that cannot be explained by local hidden variables. and these correlations are used in quantum communication. Tunneling. Particles can cross barriers with non-zero probability, enabling nuclear decay and instruments like the STM. Uncertainty and zero-point energy. Certain pairs of variables cannot both be sharp, leading to ground state energies and physical limits. Quantum statistics. Bosons and fermions behave differently, leading to lasers, the structure of atoms, and phenomena like superconductivity. Condensed matter phenomena. Superconductivity, superfluidity, quantum Hall effects, and topological states show collective quantum behavior. Quantum technologies. Atomic clocks, quantum sensors, and developing quantum computers rely on coherence and entanglement. The common thread is not mystery. It is a specific mathematical framework that predicts experimental results. When people talk about quantum physics as if it is pure paradox, they often miss how tight the connection is between theory and measurement. The most honest way to think about quantum phenomena is to treat them as patterns in nature that show up reliably when systems are small, controlled, or both. The weirdness is mostly a clash between our everyday intuition and the actual rules. If you want one image to carry forward, it might be this. Quantum physics is a theory of probability amplitudes. Amplitudes can add and cancel. This makes interference. The square of the amplitude gives probability. Measurement produces definite outcomes, but the distribution of outcomes follows from amplitudes. Entanglement links amplitudes across systems. Decoherence spreads phase information into the environment, reducing interference. Many phenomena, from tunneling to superconductivity, follow from these ideas. As research continues, new quantum phenomena are still being discovered, especially in engineered materials and in complex many-body systems. But the core set we have covered has stood the test of time and has become the foundation of much of modern technology. To see how strong the evidence is, it helps to look at a few landmark experiments in more detail, because quantum physics is not accepted because it sounds clever. It is accepted because it keeps predicting the numbers. Take atomic spectra. When researchers observed that atoms emit and absorb light at specific frequencies, they were seeing a pattern that classical orbits could not explain. Quantum theory does not just say the lines exist, it predicts where they appear. It also predicts fine structure, small splittings caused by relativity and spin, and hyperfine structure, smaller splittings caused by nuclear spin. These details depend on precise interactions. When the calculated values match the measured lines, it is not a vague match. It is a tight match. Take the Stern-Gerlach experiment, which shows spin quantization. In this experiment, a beam of atoms passes through a non-uniform magnetic field. If magnetic moments could point in any direction, you might expect a continuous spread of deflections. Instead, the beam splits into discrete components. This tells you that the magnetic moment, tied to electron spin, is quantized. The result is one of the cleanest demonstrations that nature has built in discreteness. Take interference again, but consider that it is not limited to electrons and photons. Interference has been observed with neutrons, atoms, and even large molecules. As the objects get larger, the experiment becomes harder because decoherence grows, but the basic rule stays the same. If you can keep the object's quantum phase coherent, you can see interference patterns. This tells you that the quantum framework is not a special trick for a few particles. It is a general framework. When people hear about single particle interference, they often picture a particle as a tiny pellet that must take one route. But experiments show that when the setup allows it, the probability distribution behaves as if multiple paths contribute. The wave function is not a fog of matter. It is a tool for predictions, but it is a tool that must be taken seriously because it encodes phase, and phase can change what happens. This is why it is important to understand the difference between adding probabilities and adding amplitudes. If you have two exclusive paths and you know which path occurred, you add probabilities. If you have two paths that remain indistinguishable in the relevant way, you add amplitudes and then square the result. The difference between these two rules is exactly the difference between an interference pattern and no interference pattern. Entanglement provides another strong set of tests. Bell test experiments are careful because the stakes are high. You need to randomize measurement settings quickly. You need detectors that register enough events. You need space-like separation so that signals traveling at or below the speed of light cannot coordinate outcomes during the measurement window. Modern experiments have achieved these conditions well enough that the remaining loopholes are small and do not support a simple classical explanation. The meaning is not that information travels instantly. The meaning is that the joint quantum state produces correlations that are not compatible with a picture where each particle carries a private instruction sheet that determines the outcome for every possible measurement setting, independent of what happens elsewhere. The world is more linked than that. Another phenomenon that can make entanglement feel more concrete is the way it shows up in condensed matter. In many body systems, entanglement can be spread across many particles. It can help explain why certain phases exist and how they change. In quantum magnets and topological systems, researchers use entanglement measures to understand how information is distributed in the ground state. Now return to tunneling, but connect it to everyday devices. Inside a modern transistor, especially at very small scales, tunneling can become a problem because electrons can leak through barriers that were meant to be insulating. This is one reason why shrinking transistors becomes harder. Engineers must design gate materials and geometries to reduce unwanted tunneling while still allowing fast switching. At the same time, controlled tunneling is used in devices like Josephson junctions. A junction can be designed so that pairs tunnel coherently, producing stable phase relationships. That phase can be used as a control knob in circuits. In superconducting qubits, the energy levels are engineered by combining capacitance, inductance, and Josephson effects. If you look closely, you see a pattern. Quantum phenomena are not only observed, they are engineered. The rules are stable enough that you can build technology around them. Measurement is still the part that creates the most confusion, so it is worth going deeper. In quantum physics, there is a difference between the smooth evolution of a state when it is isolated and the update that occurs when a measurement outcome is obtained. The smooth evolution is described by an equation that is linear and deterministic for the state. The measurement update is probabilistic. This is sometimes described as a split between two kinds of dynamics. One is continuous evolution. The other is collapse to an outcome. Different interpretations offer different ways to understand this split. The Copenhagen-style approach treats the quantum state as a tool for predicting outcomes and treats measurement as a special context where we speak about outcomes in classical terms. In this view, asking what the system was doing between measurements can be a poorly formed question, because the theory is built to connect preparation and measurement. The many worlds approach, by contrast, treats the quantum state as a real physical object that always evolves smoothly. In this view, measurement does not create a single outcome by collapse. Instead, it creates branching of the combined system of observer and measured object into different outcomes. Each branch contains an observer who sees a definite result. Probabilities are then explained in terms of the structure of branching and the weights of branches. Pilot wave or de Broglie-Bohm theory offers a different option. It keeps a wave function that evolves according to the usual quantum equation, but it also adds definite particle positions guided by the wave function. In this view, particles always have positions, but the wave function guides their motion in a way that reproduces quantum statistics. It is non-local because the guiding wave depends on the configuration of the whole system. Objective collapse models propose that the collapse is a physical process that happens spontaneously, not just when an observer measures. These models add extra terms or rules to produce collapse with a certain rate that becomes more important for larger systems. They aim to explain why macroscopic superpositions are not seen. Experiments can test these models by looking for deviations from standard quantum predictions. At the moment, standard quantum mechanics with decoherence explains a great deal. Decoherence shows how classical-like behavior emerges, because the environment rapidly records information about certain variables. It explains why interference disappears in practice for large systems. But decoherence by itself does not select one outcome as the only real one. That is why interpretation debates continue. Even if you do not pick an interpretation, the operational facts remain. When a measuring apparatus becomes correlated with a system, the joint state encodes those correlations. When we examine the apparatus, we see one outcome. The statistics of outcomes across many trials match the quantum rule. There is another important point about measurement. Not all measurements are the same. A projective measurement sharply distinguishes outcomes and typically destroys certain superpositions. But there are also generalized measurements that provide partial information. In quantum control and quantum computing, researchers use sequences of operations and measurements that gradually steer a system. Quantum feedback control is an example. You measure a system weakly, infer its state with some uncertainty, then apply control pulses based on the measurement record. Over time, you can stabilize certain quantum states. This is a practical art that depends on understanding measurement as an information-gathering interaction. Now consider the phenomenon of contextuality. Contextuality is the idea that the outcome of measuring a quantity can depend on which other compatible measurements are performed alongside it. In classical physics, you might assume that every observable has a value independent of what you choose to measure. Quantum theory violates this assumption in certain setups, as shown by the Cauchy-Specker theorem and related experiments. Contextuality is not as widely discussed as entanglement, but it is important. Some researchers view contextuality as a key resource for quantum advantage in computation. It also reinforces the idea that quantum outcomes cannot always be understood as revealing pre-existing values. Another phenomenon to add is quantum recurrence and revivals. In some isolated quantum systems, a wave packet can spread out and later reform, producing a revival of the initial pattern. This can happen in systems with discrete energy levels and coherent evolution. Revivals have been observed in atoms and molecules. These effects show that quantum evolution can produce time patterns that have no simple classical analog. They also show the importance of discrete spectra and phase relationships. Now shift to chemistry. The chemical bond is a quantum phenomenon. Electrons occupy molecular orbitals that are spread across atoms. Bonding and antibonding orbitals determine whether a bond forms and how strong it is. The shapes of molecules, the angles between bonds, and the energies of reactions all depend on quantum structure. Computational chemistry uses quantum methods to predict molecular properties. For small molecules, very accurate calculations can be done. For larger molecules, approximations are required. But the fact that these calculations can match experimental reaction energies and spectra shows again that quantum theory is a working tool. In photosynthesis and other biological processes, there are ongoing debates about how much quantum coherence plays a role at functional timescales. Some experiments suggest that certain excitations in light harvesting complexes may show coherent behavior for short times. Even if coherence is short-lived, it can still influence energy transfer efficiency. This is an active area of research. Now return to the idea of fields. In quantum field theory, particles can be created and destroyed, and interactions are described as exchanges of field quanta. This framework is essential for understanding high-energy processes. It also changes how we think about the vacuum. The vacuum is not a simple, empty stage. It is the lowest energy state of fields, with fluctuations that can have measurable effects. The Lamb shift and the Casimir effect are examples of vacuum-related phenomena. Another example is spontaneous emission. An excited atom will emit a photon even in the dark. This can be described as the atom interacting with the vacuum modes of the electromagnetic field. The vacuum provides available modes for the photon, and the coupling leads to decay. Spontaneous emission rates can be altered by changing the environment. Put an atom in a cavity that restricts electromagnetic modes, and the emission rate can change. This is the Purcell effect. Cavity quantum electrodynamics studies these interactions and has applications in quantum information and lasers. Now consider one more phenomenon that connects quantum rules to thermodynamics: quantum thermalization. When an isolated quantum system evolves, it can look as if it reaches thermal equilibrium for certain observables, even though the full evolution is reversible. Researchers study how and when subsystems appear thermal and how entanglement spreads. This connects quantum mechanics to statistical mechanics. Related to this is the idea of quantum chaos. Some quantum systems have dynamics that are sensitive in a way analogous to classical chaos, but the concept is expressed differently because quantum evolution is linear. Researchers look at energy level statistics, operator growth, and out-of-time order correlators as ways to quantify chaos in quantum systems. These topics are more advanced, but they show that quantum phenomena continue to produce new questions, even within the established framework. Now bring it back to the central theme. What makes a quantum phenomenon feel surprising? is often that it breaks a classical habit of thought. We are used to thinking that objects have definite properties at all times, and that probabilities come from ignorance. Quantum physics asks us to accept that the best description we have is often a state that encodes probabilities and phase, and that phase can change outcomes. At the same time, quantum physics is not a license to claim anything. It is a discipline with strict tests. If a claim about a quantum effect does not connect to a measurable setup and does not produce correct numbers, it is not physics. It is also important to separate quantum effects from exaggerated stories. Entanglement does not let you send messages faster than light. Tunneling does not let you walk through walls. Uncertainty does not mean anything can happen. The rules are exact, and the effects are typically constrained by probabilities that can be extremely small. If you keep that balance, quantum phenomena become less like puzzles and more like tools for understanding and building. Now imagine looking at the world as layers. At the scale of everyday objects, classical rules work extremely well because decoherence is strong and because the relevant variables average over many quantum events. At the scale of atoms, molecules, and engineered nanosystems, quantum effects stand out. At the scale of very high energies, quantum field theory is needed. Across all these layers, the same underlying quantum framework applies. And if you want to end with one practical reminder, it is this: quantum physics is already in your life. Every screen, every light, every chip, every GPS signal, and every modern medical imaging system depends on quantum phenomena. These are not rare events at the edge of science. They are the working rules of the material world. To make that feel less abstract, consider a normal smartphone camera. When light enters the lens, it lands on a sensor made of a semiconductor. Photons are absorbed and create electron-hole pairs. Those charges are collected and counted. The entire process depends on band gaps, quantized energy levels in solids, and the probabilistic absorption of photons. Consider a GPS receiver. The receiver relies on timing signals from satellites. The timing itself is anchored by atomic clocks, which use precise quantum transitions. GPS also requires relativity corrections, but the clock that makes the timing possible is quantum. Without quantum timekeeping, the system would drift quickly and positioning would fail. Consider a laser pointer. The coherent beam comes from stimulated emission, which depends on quantized energy states and population inversion. The beam quality depends on cavity modes, which are standing wave patterns of the electromagnetic field, a field treated quantum mechanically at a deep level. Consider a computer processor. Transistors in the chip depend on semiconductor physics. At small sizes, engineers must also manage quantum tunneling and quantized conductance effects. The chip is designed with classical logic, but its physical operation depends on electrons that obey quantum rules. Consider medical imaging. MRI depends on nuclear spin transitions and on how spins interact with magnetic fields and their environment. PET scans depend on antimatter annihilation and photon detection. X-ray imaging depends on how high-energy photons interact with matter. Many techniques rely on quantum interactions, even when the user interface looks simple. Now consider a more subtle, everyday quantum phenomenon: stability. The fact that solid objects are solid is tied to quantum statistics. Electrons are fermions. The Pauli exclusion principle prevents them from all collapsing into the lowest energy state. This creates a structure of electron shells and a resistance to compression. In a very deep sense, the shape and size of matter depend on quantum rules. Even sound and heat in materials connect back to quantum physics. Vibrations in a lattice are described as phonons, saga quantized modes of vibration. Heat capacity at low temperatures follows quantum predictions. The way heat moves through certain materials depends on how these quantized modes interact. Now imagine the near future. Quantum phenomena are being turned into new tools. Quantum networks aim to distribute entanglement across distances. Quantum key distribution can provide security based on physical principles rather than computational difficulty. Quantum sensors can measure gravity gradients for mapping underground structures. Quantum computers aim to simulate molecules and materials directly. Whether every promise will be reached is still unknown. Engineering is hard. Noise is stubborn. But the trend is clear. Quantum physics is shifting from a theory that explains strange lab results into a set of methods that can be used intentionally. There is also an educational lesson in all of this. The quantum world can feel strange because it does not match the shortcuts that the human brain uses for everyday prediction. The brain learned to track objects that are large, warm, and constantly interacting with their environment. It learned to treat them as having definite properties. It did not evolve to track phase in probability amplitudes. Once you accept that, the confusion drops. Quantum physics is not asking you to accept anything without evidence. It is asking you to use a different kind of model, because the old model fails at small scales. The new model is harder to picture, but it is more accurate. If you keep the focus on experiments, the story becomes steady. Quantization shows up in spectra and devices. Interference shows up in patterns that can be predicted and controlled. Entanglement shows up in correlations that violate classical bounds. Tunneling shows up in decay rates and in microscopes that can image atoms. Uncertainty shows up in ground state energies and in limits to measurement precision. Statistics shows up in the structure of matter and in the behavior of materials at low temperatures. The list is long, but the logic is consistent. Quantum phenomena are a set of linked effects that follow from a few core principles, states that encode probabilities and phase, linear evolution that allows interference, quantized interactions, and measurement outcomes that are discrete. It also helps to remember how the field kept itself honest. When early quantum ideas appeared, they produced numbers that could be checked. The Rydberg formula for hydrogen lines could be measured. The spacing of Landau levels could be measured. The quantized Hall resistance could be measured. The behavior of superconductors could be measured. Over and over, the theory survived contact with instruments. The instruments themselves became part of the story. Better vacuum systems made interference experiments possible with larger objects. Better cryogenics made superconducting and quantum Hall effects easier to study. Better lasers made precision spectroscopy possible. Better electronics made single photon detection and fast random measurement choices possible in Bell tests. So quantum physics is not just a set of ideas. It is a partnership between theory and hardware. Each time the hardware improved, it became possible to test a more delicate prediction. And each time the prediction held, confidence grew. And if you ever feel tempted to treat quantum physics as a word that explains anything, It helps to return to the test. A quantum claim must be tied to a setup you can build, an outcome you can measure, and a prediction you can compare against data. If it cannot be tested, it does not belong in the same category as the phenomena we described tonight. This discipline is what turned early confusion into one of the most successful theories in science. It is also what keeps the field moving forward now, as researchers push coherence longer, scale entanglement to more systems, and search for new phases of matter where quantum rules show up in fresh ways. In the coming years, some of the most interesting progress will likely come from places where quantum effects meet complexity. That includes many body systems where huge numbers of particles interact, leading to behavior that is not obvious from the parts alone. It includes new materials where topology protects surface states. It includes hybrid systems where light, mechanical motion, and superconducting circuits interact. It also includes precision tests that look for tiny cracks in the standard quantum description, not because the theory is weak, but because the best way to learn more is to push where the theory is most precise. Even if the core framework stays the same, the map of what quantum systems can do keeps expanding. Every new stable qubit, every more sensitive interferometer, every cleaner material, and every better detector adds another place where the small-scale rules can be seen directly. One last thought to keep it grounded. The quantum world is not separate from the ordinary world. The ordinary world is what quantum rules look like after countless interactions have averaged out the phase information that drives interference. In most daily situations, objects are warm, noisy, and constantly colliding with their surroundings. So coherence is lost almost instantly, and the results look classical. But when conditions are right, coherence can be protected long enough to matter. That is when you see the underlying layer in a clean way. You see it in an interference pattern that builds dot by dot. You see it in a tunneling current that changes sharply with distance. You see it in an energy gap that turns resistance off. You see it in correlations between distant measurements that beat any classical bound. And because these effects can be predicted and repeated, they are not just stories. They are features of nature that can be used, tested, and built into devices. If you remember nothing else, remember that quantum phenomena are real experiments first, and strange language second, with measurable, checkable results. This was a quiet archive story, where the story ends, sleep begins,